Knowledge about spontaneous fission comes from experiments conducted with californium-252 and nobelium-252, both of which can be obtained in large volumes, as well as from a very small amount of fermium-258, where unusual fission is observed. Superheavy elements appeared here, and they also end at spontaneous fission, as you can see. This immediately increased the scope of research in spontaneous fission, and in my opinion, there are two types of research. You can see that this zone of green color appears here in the region of elements 110, 111, 112, and 114. This is spontaneous fission of fairly heavy nuclei, and it also appears here in the region of elements 104, 105, and 106. These nuclei are located near the spherical shell, while these nuclei are in the region of deformed shells. Such a large range of nuclei can be studied, and we can expect completely different modes of spontaneous fission. These fissions may or may not be asymmetric. They can also be symmetrical, which I will now explain in more detail. We know that actinide nuclei, such as uranium, when irradiated with thermal neutrons and fission spontaneously, have asymmetric fission. This is the spectra of a light fragment, and this is the spectra of a heavy fragment. The kinetic energy of these fragments is 168.5 mega-electron-volt. And this asymmetric fission is due to the magic effect manifested in the fragments. If there was a liquid drop or no structure, then the fission would be symmetric. But it is asymmetrical. Withdrawing this magic effect will allow us to carry out a very difficult experiment by removing the largest kinetic energies so that the nuclei would not be excited, and then we will achieve the so-called cold fusion. As soon as the nucleus moves beyond the barrier, it immediately divides. We will, of course, compensate for this with efficiency, which can go down by 6 orders of magnitude. This remarkable experiment was carried out in France. As you can see in the graph, uranium fission degenerates. The kinetic energy here increases up to 194 mega-electron-volt. The maximum it can be is 196 mega-electron-volt in this zone. But we can clearly see that this peak here is due to the fact that the doubly magic nucleus of tin 132, with its 50 protons and 82 neutrons, as well as its neighbors, each of which has either proton or neutron magic, are active. When we move on to the heavier nuclei, this is uranium. From the nuclei of the 92nd up to the nuclei of the 104th element, we can see an effect that has not been observed before when people worked with actinide nuclei. Indeed, it was shown that the effect of the tin 132 shell leads to the fact that the heavy fragment changes little, and the light fragment, as the nucleus becomes heavier, increases exponentially. At some point, they will converge. When they converge, it will be symmetric fission. And this will happen at Fermi 264, which will have 100 protons and 164 neutrons. Then we will have an exact division into 2 doubly magic nuclei. That is just the way in which it divides. In fact, it turned out that already at fermium 258, the fragments change over to symmetrical division. This was observed not only at fermium 258, but also at mendelevium 260, not yet reaching fermium 264. But we now have the opportunity to pause here, where there is Rutherfordium-268 and Dubnium-268, the same dubnium and Rutherfordium which we isolated chemically. This dubnium can have symmetric division, or, as we like to call it, supersymmetric division, which I will soon show you. Then, in relation to uranium, it would look quite exotic. It would have a huge kinetic energy, 248 megaelectron volt, and there would still be a decent amount of energy left for neutrons to be emitted. As we have seen, there was a large amount of kinetic energy, and 4 neutrons were emitted. And these are the results of the calculations by Nikolai Karjan, a well-known theorist in the field of nuclear fission. And according to his calculations, as we move towards more and more artificial nuclei, for example, starting from fermium-246 or 248, or even 250, they gradually align, as you can see. Then they will merge, and already at fermium-258, which has 2 times 50 protons and 2 times 79 neutrons, this fission becomes symmetric. Nikolai states that this is not the limit. Should we continue along this path, this peak will become even narrower. Finally, you will arrive at fermium-264, where it is quite narrow. But it is not possible to reach this point because we need to obtain a nucleus which has fragments and which will have 2 times 50 protons and 2 times 82 neutrons. But there is another option, which is associated with super-heavy nuclei. If americium is irradiated with calcium-48, you might remember these 5 decays. Then dubnium is formed, and then it undergoes electron capture before Rutherfordium is obtained. Here it is. Rutherfordium has 2 times 82 neutrons and 2 times 52 protons, which is much closer to this supersymmetric combination than it was at fermium-258. I would like to point out that this is not the limit, because Rutherfordium-270 can also be produced with 2 times 82 neutrons and 50 protons in each fragment. I would also like to point out that if an alpha particle is emitted from such a nucleus, then we would definitely have this nucleus plus an alpha particle. It may very well be that for this nucleus, the probability of triple fusion with the emission of an alpha particle will be high, because here we obtain fission in the form of 3 magic nuclei, twice tin-132 plus helium-4.